All right, so page 5 in your notes. Yesterday we talked about molarity. What can you tell me, just to recap, what can you tell me about molarity, guys? What is it? What does it measure? Let's start there. Moles per liter, which is a concentration. All right, so the higher that number, the more concentrated it's going to be, meaning it's stronger. So if you see something like the stock acid that I have in my cabinets in the back is something like 12 molar hydrochloric acid. That stuff, if I left it on the floor, it would eat through the floor eventually. Okay? No, we're not going to do it. Okay? All right? Just a small spot, small spot every year, then I've got a big spot over time. Yeah, no. Just for your class. Yeah, no. Obviously, guys, I don't want to use, or we have no purpose of using that strong of acid in any regular ordinary chemical reactions like that we're going to do in here. You're never going to use something that strong. Right? So what I have to do is I've got to dilute it. What does diluting mean? To dilute something. Yeah, you make something less strong. Not just adding water. Now, in our class, that's the solvent we're going to use is water. But really, it's just adding more of your solvent. And what's that going to do to the concentration? Yeah, it weakens it, right? It sort of, quote unquote, waters it down. So maybe you've heard that term like, oh, populations get diluted, or, there's a big rush for like pharmacists and stuff. And that's been it's a lot harder to get into like pharmacy school than it used to be because it's diluted. More people are trying to do it. So it's become much more competitive. All right? So this formula, guys, allows us to figure out concentrations from dilutions. A lot of times you'll hear them called serial dilutions, all right, where they kind of go down in a series, in a stepwise pattern. Okay. Often these are performed for acid-base chemistry, which is our next unit. So I may have you guys do a set of serial dilutions in the next few weeks. And why would we want to dilute something? It's just so it's more manageable, easier to use. So it's not stronger. That we could, we're not going to harm ourselves or something like that. In industry, yeah, they're using the strong stuff potentially. In different cleaning applications of, industrial processes, they use strong, concentrated things. But in everyday use, we don't want that. M1V1 equals M2V2. What formula does this look like? This is a review question. Alex? Boyle's law, right? Boyle's law was what, guys? P1V1 equals P2V2. So what type of relationship is this? If we know that. Yeah, this is an inverse or indirect relationship. Maybe you want to jot that down. The graph for this would look something like this. As molarity goes up, volume will go down. Now, we typically, our first one, guys, our first molarity is going to be stronger, and we're going to try to dilute it to make this weaker. So if this one's higher and this one's weaker, that means your volume typically is going to go up. So when I buy a set of, or a bottle of strong hydrochloric acid, it's typically like 2.5 liters worth. I'm probably not going to have to buy that again for a really long time, if ever, because I'm going to dilute that down to something that's much less, which is going to make a higher volume in the end. Okay? So one bottle will actually last me, probably last me my career here. It wouldn't surprise me as much as I'm going to use it. So this formula, this should not be much more, this shouldn't be that difficult for us to use because we've used a formula just like it. The units are the only thing that's going to be different. So let's take a look. How much 12 molar HCl is required to prepare 300 mils of a 5 molar solution? So again, jot down your important pieces of information. M1 equals 12 molar. V1 equals, do we know V1? No, that's what we're looking for. This is typically, guys, going to be the way you use this formula. Okay, you know your starting concentration. You know what type of solution you want to get to. So when I go to make solutions later this week for our acid-base unit, when we do what's called a titration, all right, I've got to take some of that stock and I've got to dilute it down. I know the volume I want to get to. I know the concentration. So what I'm looking for is going to be V1 because that's how much of the strong stuff do I need to start with to then dilute it up to that volume. So molarity 2 is going to be 5.0 molar. V2 is going to be 300 milliliters. Okay? M1V1 equals M2V2. Get your reference packets out as well. All right, I want to show you that you have a couple of these formulas.
Oh, so you don't have to convert it to liters?
We hadn't got there yet. Jill brings up a great question. She says, oh, we don't have to convert it to liters. Do we or do we not? Yeah, guys, we do need to. Why? Because our molarity, I didn't write it out this way on purpose. What does molarity mean? It means moles per liter. So we have to have our volume in liters. That's easy. How many liters do I have here? 0.3 liters. Okay, that's simple. I'm looking for V1. I'm going to get it by itself. Again, the more work you show me, the more partial credit I can give you if there's a mistake. So M2, V2 over M1. So we've got 5.0 multiplied by 0.3 divided by M1, which is 12. V1. 5 times 0.3, that's 1.8 divided by 12. What do we get for a final answer? Let's think about it. Guys, my concentration went down, all right, which means my volume would have to go up. So my volume that I had in V1 should be lower than V2. How much do I have? How many milliliters is that? Yeah, 125 milliliters. So, here's a little hint. Actually, no, I don't even want to say it. I'm not even going to. So, 125 milliliters, guys, 0.125 liters, they mean the same thing. Easy? I should hope so. I want you guys to try the you try problem. It is. Yeah, don't make it harder than it needs. We've already done this math before, so we're just doing a couple problems. We will use this quite a bit, like I said, because it's something super applicable. This is something I did all the time when I was in grad school or working in the lab. So 0.035 liters. That's the biggest thing, guys, is make sure that you're converting it correctly. If you're not doing the math out, make sure that you're moving the decimal appropriately. M1 equals 15 molar. Now think about it. M1 should always be what in comparison to M2? M1, guys, is always going to be higher than M2 because, again, you're diluting it. Diluting means to weaken something. So your starting molarity should be stronger than your final one. M2 equals 6 molar. V2 equals question mark. M1, V1. M2, V2. All right, get V2 by itself. So I'm just going to plug it in. 15 molar times V1, 0.035 liters, all over M2, 6 molar. What do we get for volume 2? It should go up because our molarity is going down. What did you say, Grant?
87 milliliters.
So 0.0875 liters, or like he said, 87.5 milliliters. Do we have to go back to milliliters? No, you don't have to, but if you want to, okay, because that's what you started with, that's fine, unless it says to go back to. So on your Regents exam, be on the lookout for what unit it's asking you for. That's an easy way they're going to get you to trip you up. You know what to do, but you've got to make sure that you read and answer the question that's asked. Questions? All right, there's a couple other concentrations that we need to talk about that you need to be aware of. The first one is mass percent. Guys, we've already done this as well. Okay, we've done percent composition. Remember that back in Unit 6? We did percent composition of bubble gum. What's our general formula, guys, for percent composition by mass? Alex? Part over whole times 100. Same thing, guys. In this case, it's the mass of our solute divided by the mass of the entire solution. Okay? So it's still the same thing. And then I believe we need to multiply by 100 there to get a percentage. So simply, the mass of an ingredient divided by the total mass of the solution expressed as a percent. It's the same as what we did in percent composition. So there's an example. I want you guys to go ahead and try this. But there's a catch. Actually, I just remembered. What's the percent by mass of sodium hydroxide if 2.5 grams of NaOH are added to 50 grams of water? We have to identify the two pieces, right? So if we take a look, guys, at percent mass, so percent mass equals, if we look at our formula, mass of solute over, what's it say? Solution. Okay, times 100, that gives us our percentage. So we got to figure out what's our solute and what's our solution.
Solute is sodium hydroxide.
How do you know that, Garrett? How do you know it's sodium
It
hydroxide?
says what percent mass of sodium hydroxide if 2.5 grams of sodium hydroxide are added.
Added, right? That's the key. Guys, remember, this is where knowing your definition, your vocab. So I'm having a vocab quiz. Okay, solute is what you add to the solvent. Okay, so you're adding the sodium hydroxide. That's how you know that this is your solute. So our mass of our solute is 2.50 grams. Okay, what's my solution mass? Yeah, why is it the 2 added? Because what's our definition of the solution? Yeah, it's the mix of the solute and the solvent. That's the piece that people will forget. And I speak from experience. When I was in your seat, guys, 10 years or so ago, I messed that up all the time because it was going quick. You've got to add up both masses. The mass of the water, which is the solvent, plus the mass of your solute. So what's our total solution mass here?
52.5.
Yeah, 52.50 grams. All right. Now it's pretty simple. So our percent mass equals 2.50 grams divided by 52.50 grams multiplied by 100. Percent mass is going to equal, do the math. What do we get here? 4.8, 4.76. All right, same thing. Remember, you multiply by 100, so it's not the 0.048. You got to remember to multiply by that last piece of 100. All right, but we've done this already, guys. The new piece, the one little new piece, is you've got to be able to identify which is your solute. That's, again, the thing you're adding to your solvent. And then you've got to make sure you add both the solvent mass and the solute mass together to give you your solution mass.
Shouldn't it be pretty easy to figure out with the solute?
Oh, yeah. Yeah, that could be the case. But really, look for that keyword like added to or mixed with something. That's going to be, typically it's not going to be water. I would imagine as I look through more Regents exam questions as we move toward the end of the year, I would bet that they're only going to give you water as a solvent. I mean, I don't think we'll ever use anything besides that. So know that water, hey, is what you're mixing it with. Whatever the other substance is, that's going to be your solute. Is a good rule of thumb. Yeah. And as I look through more questions, if I see something where it's not like that, we'll do that problem together just to make you guys aware of it. All right, so that's percent mass. Very similar, guys. The other one we're going to talk about that you need to be aware of for your Regents exam is parts per million. All right. This is similar to percent composition. It's a ratio between the mass of the solute and the total mass of the solution. That got cut off. This should actually be. Is that in your notes like that? The solution, if it's bolded, that should be up there. Did I mess that up? No, it's good in your guys'. All right, it's just my slides. This is used for extremely dilute solutions, guys, when molarity and percent mass just are too difficult. So, have you guys ever heard of parts per million concentrations before?
Yeah.
Where have you heard it, Grant? Any ideas? No? But you've heard of it, right? A typical one is every year, I don't know if you are aware of this, but your parents in the mail will get like a water quality report. Okay? That the whatever municipality you live in, they send that out saying, hey, it's been tested, this is what we found. Parts per million, guys, is a great example of where you would see, with water qualities, where you'll see parts per million. you have to have certain levels of, different things in there. Like you want to make sure, lead is below a certain parts per million. I wish I had it this year, but there's a container. If I can get it, I will. Otherwise, I'll probably have it next year. That has like parts per million. It kind of shows you that, but I'll look for a picture or something like that. The only difference, guys, in finding this is that you multiply by 1,000,000 instead of 100. It's the only thing that's different, okay? And these values are going to be very, very dilute. So you're going to see very small pieces. So take a look right here. Look at our masses. All right, something super, super tiny. So approximately 0.0043 grams of oxygen can be dissolved in 100 mils of water at 20 degrees Celsius. Express this in terms of parts per million. So what's my solute? Oxygen, right? It's being dissolved in water. So it's 0.0043 grams of oxygen dissolved in 100 mils of water. When we look at this formula, guys, for percent or parts per million, it's mass of solute over total mass of the solution. Is milliliters a mass? No. How can we figure that out? Molar mass, but what's something unique about water? What's the density of water, guys?
1 gram.
Right. 1 gram per mil. So however many mils we have, how many grams do we have? Oh, yeah, it's the same amount. So we have 100 grams of water. So what's my total mass of my solution?
100.004.
Yeah, exactly. All right, so it's really not going to impact it much. That's why we use parts per million. So we're going to figure it out the same way. ppm equals, I'll say it again, mass of solute divided by mass of solution times 10 to the 6th, right? That's 1,000,000. 10 to the 6th. So ppm is going to equal 0.0043 grams divided by 100.0043 grams times 10 to the 6th. Go ahead and do the math. So we'll call it 43 ppm is our concentration, 43 ppm. Do you think it's always going to work out that way? Oh, I can just take 43. No, it worked out that way, guys, because it was 100 mils of water this time. So always do the math. Don't just assume. Is this stuff anything super brand new? No, it's not, guys. And if you take a look on your reference packets, if you look on your table T, okay, you have the parts per million formula given to you. You have molarity given to you. You do not have M1V1 equals M2V2, which I'm surprised, but your titration formula is similar to that, so it can help you remember. I want you guys to add under concentration, add M1V1 equals M2V2 to yours. Okay, add that in there.